In this section, hopefully this section should be relatively easy and sort of a review, only because in the last section we did 5.2, we did sample proportions, and this section is basically the same concepts, only we're going to be talking about means specifically instead of proportions. All right, so after this section, what should you expect? You should be able to expect to be able to find the mean and standard deviation of the sampling distribution of a sample mean. So last section we did sampling distribution of a sample proportion. Here we're doing a mean. We're going to be able to check the 10% condition before calculating the standard deviation of a sample mean. So hopefully that rings a bell. That's the same as the last section. We're going to explain how the shape of a sampling distribution of a sample mean is affected by the shape of the population distribution and the sample size. If appropriate, we're going to use normal calculations to calculate probabilities involving sample means. All right, so sort of the same process that we did in the last section and the same process that we use. Just take a minute and do a quick refresher of the sampling distribution of X bar. All right. So what exactly is the difference between a sampling distribution of means and a sampling distribution of proportions? So sample proportions arise most often when we're interested in categorical variables. Okay, so this is the proportion of people that have red hair, the proportion of people that think they're sexy and they know it, the proportion of people that are the proportion of orange Reese's Pieces in a Reese's Pieces bag. Okay, so we're looking at categorical variables. Remember, variables that you can't really do any math on. Sample means are used in quantitative variables when we're interested in other statistics such as the mean or median or standard deviation. So when we look at the mean, we might find the mean height of all the students in Fairfax County. We want to maybe find the mean number of miles each student has to go to get to school in Fairfax County, the mean amount of time commuting to school, the mean number of time students waste in a classroom, the mean number of minutes in between classrooms. Okay, so those are all quantitative variables that we can do math on. All right, so let's just take a look at a quick example. Let's consider the mean household earnings for samples of size 100. We're going to compare the population distribution on the left with the sampling distribution on the right. Okay, so what is the difference between the population distribution and the sampling distribution? All right, so the population distribution, what the population distribution did is they found, let's just say this is in Fairfax County. So we found all of the household earnings in Fairfax County and put all of those household earnings on this graph. Okay, I went to every single house in Fairfax County. So each of these are all individual values. These are all individual households. All right, take a look at it. The distribution honestly is skewed a little bit right. Okay, so the median would be the better measure of center, and here's the mean. It's pulled down by the tail. How is that different from the sampling distribution? Okay, so the sampling distribution is not individual values, it's a bunch of X bars. Okay, so what that means is I went around, all right, and I got 100 households and I found the mean. I went around, I got another 100 households and I found the mean. I went around and got another 100 households and I found the mean. I went around and got another 100 households and found the mean. All of those means are what is in this graph. Okay, it is not individual values, it's a sampling distribution because it is all of the means on my distribution are put on my graph. Okay, notice, look at the bottom, this just says household earnings, so that's individual values versus mean household earnings for samples of size 100. Okay, take a look at this distribution. This distribution is a little bit more approximately normally distributed. It's unimodal, it's symmetric. Okay, so let's just take a look at that for a minute and sort of compare the center and the shape. So what did we notice about the shape? We said that this one was sort of skewed to the right. Okay, that's the population distribution, where this one, our sampling distribution, was approximately normal. All right, let's take a look at the center. So the center here is sort of pulled down. The mean is pulled down. So the median would actually be a better measure of center, where here the mean is going to be a good measure of center since it's approximately normal. Also, take a look at the spread. The graph that is skewed to the right has much more variability than the sample-ling distribution. The sample-ling distribution has a very small variability within my graph. Talked about the center, the shape, and the spread. So let's take a look at both distributions. Okay, so let's take a look at the population distribution. So both distributions are centered at the mu, here's your mean right here, which is $69,750. So over here, same thing, if I were to draw the mean in the middle, okay, so that mean would be same thing, $69,750. Okay, now we didn't say that the mean was the best measure of center for the population distribution, it's just what the mean is. The shape of the distribution is strongly skewed to the right. However, the sample-ling distribution is symmetric. So here we have our symmetric distribution where this one is skewed right. Okay, the spread of the distribution of earned incomes is pretty spread out. So we're going from 0 all the way to about 250, whereas the spread for my sample-ling distribution is maybe from like 50 to 100. So that is a much smaller spread. So if you notice, the sample-ling distribution does not necessarily model the population distribution. They're not equal, so they're different. The only thing that's the same right here is that they both have the same mean. Okay, everything else is different. One is skewed right, but the sample-ling distribution is approximately normal, and the spread is much smaller for the sample-ling distribution instead of the population distribution. Think about it for a minute, and why would the sample-ling distribution have a smaller spread than the population distribution? Okay, we'll go over that in a minute, but I just kind of want you to think about that in your head. What does all of that mean? Let's just make sure you understand the difference, okay? Please make sure that you understand that the facts about the mean and standard deviation of X bar or my sample are true no matter what shape the population distribution has. So we're going to take a look at the mean and the standard deviation of the sample-ling distribution. So this is of the sample-ling distribution. They are always going to be true no matter what shape the population distribution has. So if you remember from the previous slide, the population distribution was skewed to the right. However, my sample-ling distribution was approximately normal. Okay, so when we choose many simple random samples from a population, the sampling distribution of the sample mean, so why is it the sampling distribution of a sample mean? Because the graph that I have created is not individual values, but it's a whole bunch of averages of individual values, okay? All right, the sample is centered at the population mean mu. All right, so they do have the same population means. So if I was going to take basically the average of the averages, okay, the average of the averages will have the same mean as the population. The sample mean is less spread out than the population distribution. So that's saying that the sample-ling distribution has a smaller spread, okay? So basic facts about the sampling distribution of a sample mean. Okay, let's suppose that X bar is the mean of a simple random sample of size n drawn from a large population. So we know the population is mu and the standard deviation is sigma. Okay, so remember this is your X bar is from the sample, mu is from the population. The mean of the sample-ling distribution of X bar is the mu of X is equal to mu. Okay, so what does all that mean? That's like saying, here's my sample-ling distribution up here. That's like saying the mean of this sample-ling distribution, so like the average of all of the averages, is going to be the same as the mean of the population. Okay, how do I then get the standard deviation? Well, the standard deviation of this graph, okay, is going to be smaller. So the standard deviation of your sampling distribution is going to be smaller. So how do we get that smaller value? We're going to take sigma, our population standard deviation, and divide it by the square root of n, or our sample size for each of these individual samples. Okay, so the standard deviation of the sampling distribution is the sigma of X bar is sigma over the square root of n. So this is really important. This notation, mu of X bar, is equal to, you're going to write a number there, and then the standard deviation of x bar, you're also going to write a number there. Why would I just not write the mu and the standard deviation? Well, what is different about those two? When you write the mu of x bar and the standard deviation of x bar, that's telling me that I'm looking at a graph with a whole bunch of means. If I just write mu and sigma, that means I'm looking at a graph of individual values. I didn't take any means. So be really, really careful with that notation. I just wanted to leave those up there for a second so you could see them. Okay, so if you need to take a minute, pause it, and then take a look at the answers. Okay, so what was the mean of the sampling distribution of x bar? Since x bar is an unbiased estimator, so by unbiased, it means that it doesn't consistently overestimate or consistently underestimate. And as unbiased estimator of mu, then the mean of the sampling distribution is equal to the mean of the population, which is 19.3 movies. So that's why I had you circle that 19.3 movies. So why would I have you circle the 19.3 movies? So you know that's an important number in order to answer your question. So what's the standard deviation of the sampling distribution of x bar? Okay, number one, you have to check that 10% condition in context. Okay, so the 10% condition is met because there are more than 10 times 100 or 1,000 high school students. So in context. So then what's your standard deviation? Notice the notation. Standard deviation of the sampling distribution is equal to the population standard deviation over your sample size, over the square root of your sample size. So 15.8 divided by the square root of 100 is 1.58 movies. Okay, so if I were to draw a graph of this, okay, these would be all x bars. The sample mean number of students, there would be 100 students in each of these x bars, and on average, how many movies do they see? The mean of all of these students would be 19.3 movies, and then the standard deviation would be 1.58. Okay, so let's just talk about what sampling distribution looks like from a normal population. So that first example we looked at wasn't from a normal population, it was from a population that was skewed to the right. So we've described the mean and the standard deviation of the sampling distribution of the sample mean x bar, but not the shape. Okay, so we've specifically talked about, okay, how do we find the mean and standard deviation from our sampling distribution? Okay, now, if you have a mean and standard deviation of your sampling distribution, but the sampling distribution is not approximately normal, we can't use the z-scores that we used in the last section. Okay, so how can we determine whether or not we have an approximately normal sampling distribution so that I can use z-scores in order to make inference about the population? The shape of the distribution of x bar depends on the shape of the population distribution. Okay, so how can we determine whether or not it's approximately normal? Now, if we take a look at a sampling distribution and we look at the means that are from a normal population, then your sampling distribution is going to be normal. So suppose that a population is normally distributed with mean mu and standard deviation sigma, then the sampling distribution of the mean will have a normal distribution with mean mu and standard deviation sigma over the square root of n, provided the 10% condition is met. So that's one of our conditions that we have to use in order to use that standard deviation. Okay, so really what this is saying, this is just saying if I have the population, if my population, this is all my individual values, so if the population for the number of movies that we see in a year is approximately normal, remember, nothing is perfectly normal, then the sampling distribution is also going to be normal. So I take a sample of 100 students, ask the mean number of movies. Another sample of students, ask the mean number of movies. The sampling distribution will also be approximately normal. Okay, so that's really all that's saying. Sorry, that just covered that up. Okay, so note that the mean and standard deviation are true if the population is normally distributed. So if the population is normally distributed, no matter what size sample, the sampling distribution will always be approximately normally distributed. So no matter what, if the population is normally distributed, most population distributions are not going to be perfectly normal. All right, so that's really not a real world situation. Okay, so what is the shape of the sampling distribution of sample means if the population distribution isn't normal? So remember, I can only use these scores if my sampling distribution is normal. My population is normal, sampling distribution is normal, population not normal. Well, what do I do? Okay, it is a remarkable fact that as the sample size increases, okay, and by sample size, I mean we're taking samples of 100 students versus samples of 5 students. So if the sample size increases, the distribution of sample mean changes its shape. It looks less like that of the population and more like a normal distribution. So think back to that first example when we had the salary. The actual distribution of the population was skewed to the right, but we had samples of size 100, and since it was so large, the sampling distribution looked like a normal distribution. So when the sample is large enough, the distribution of the sample means, so your sampling distribution is very close to normal, no matter what shape the population has, as long as the population has a finite standard deviation. So as long as, your standard deviation isn't a billion, okay, the sampling distribution will be approximately normal if you have a large enough sample size. Okay, so what exactly does the sample size have to be in order for the sampling distribution to be normal? This is where your central limit theorem is going to come into play. So if we draw a simple random sample of size n from the population with mean mu and infinite standard deviation and finite standard deviation sigma, the central limit theorem, you can abbreviate that by CLT, says that when n is large, the sampling distribution of the sample mean is approximately normal. So sampling distribution is normal if the population is normal or if I have a large enough sample. Well, how big does that sample need to be? The central limit theorem says how large a sample size n is needed for the sampling distribution to be close to normal. It does depend on the shape of the population. So more observations are required if the distribution is far from normal. So if you have a distribution that's super skewed to the right or super skewed to the left, the sample size that you're taking the means of every time is going to have to be larger than one that's just slightly skewed to the right or left. But all right, what is the general rule? So I don't want to evaluate every time. The general rule is that in most cases, if your sample size is bigger than 30, the central limit theorem will apply, and it will state that your sampling distribution is approximately normal. Okay? Let's just take a minute and look at the central limit theorem. Okay, so let's consider the strange population distribution from Rice University sampling distribution applet. All right, so this is just a random sampling distribution. N is the number of samples for the sample mean. All right, so N is equal to 2. So that just means I took a sample of 2, found the mean. Took a sample of 2, found the mean. Took a sample of 2, found the mean, put them in a sampling distribution. Well, what does that look like? Okay, so this was my original distribution. This is totally not normal at all. So I took a sample of size 2, found the mean, put it in here, put it in here. So these are all samples of size 2, found the mean. So what do we notice? Let's take a look at the shape of the sampling distribution as n increases. So as I take larger and larger samples. All right, so this is n equals 5. So I took a sample of 5, found the mean. Took a sample of 5, found the mean. I put all those means in this graph. Then I took a sample size 10, found the mean. Put the mean in the graph, 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 okay? Ooh, now we're getting somewhere here. Let's take a look at the last one. N equals 25. So N equals 25 means I took a sample of 25, put the mean in. Took a sample of 25, put the mean in. Took a sample of 25, put the mean in. Notice as my sample sizes get larger, I start out with this crazy graph with 3 modes, a bunch of gaps in it, and as my sample size increased, I have a distribution that's approximately normal. So the central limit theorem, I have this crazy graph to start with, and it only took me 25 samples in order to make it approximately normal. So the normal/large condition for sample means tells us if the population distribution is normal, then so is the sampling distribution of X, okay? If the population distribution is not normal, the central limit theorem tells us that the sampling distribution of X bar will be approximately normal in most cases if n is greater than or equal to 30. Okay, so even in this crazy case, once I got n equal 25, it's approximately normal. Why do we need the central limit theorem? Well, I sort of already touched on that. What does it allow us to do? The central limit theorem allows us to use normal probability calculations, remember those z-scores, to answer questions about sample means from many observations, even when the population distribution is not normal, as long as the sample size is larger than 30. Okay, so in the last section with proportions, before we did anything, we had to check our conditions. So what are the conditions again? Conditions are making sure you can use your standard deviation, making sure that it's a simple random sample, because we need to be able to remember a sample has to be random in order to do inference. And then we have to make sure that our distribution is approximately normal. Okay, so 1. Okay, what conditions do we need to check? We need to make sure we have a simple random sample. It's usually stated in the problem. This allows us to do inference. 2, the 10% condition. The sample must be smaller than 10% of the population. This proves independence and allows us to use the standard deviation in the normal calculations. 3, we need to make sure that the sampling distribution is approximately normal. If the population is normal, the sampling distribution will be normal. However, maybe we don't know what the population distribution looks like. However, if each sample is greater than 30, then the sampling distribution will be approximately normal by the central limit theorem. Okay, so that means, okay, when I say greater than 30, okay, so that means I have a sample size 30 and I found the mean, a sample of size 30 and I found the mean, sample of size 30 and I found the mean, sample of size 30 and I found the mean, sample size 30 and I found the mean. So hopefully by now you guys are understanding the idea of sampling distributions. Okay, now note this is different from sample proportions. This is the same for sample proportions. That applies basically to anything. If the population is approximately normal, then your sampling distribution will be. However, this is different. With proportions, what did we have to do for proportions? We had to say that our sample size times the probability of success was greater than 10, and we had to say the sample size times the probability of failures was greater than or equal to 10. They are two completely different things, okay? This is like a scale where it balances out the successes and failures and makes it approximately normal. Only use the central limit theorem with means. It does not apply to proportions. So just a couple of things. The central limit theorem does not describe how the variability of a sampling distribution increases. So it tells us nothing about the standard deviation. It literally just tells us if something's approximately normal. It is true that as the sample size increases, the variability decreases, but that has to do with the standard deviation, not the shape of the data. That has to do with your sample size, because your standard deviation, when you're dividing by the square root of n, larger sample size, okay, makes the denominator larger, but your number smaller. The central limit theorem is only about the shape of the sampling distribution, not the spread. All right, let's just do a quick summary and then take a look at some examples. All right, let's just suppose I randomly select 100 seniors in Virginia and record everyone's GPA. Oh, this look familiar? I'm interested in knowing the average GPA of a senior in Virginia. So in the last section, we looked at the proportion of seniors that were greater, that had a GPA greater than 2. Okay, that was a proportion. This case, we're looking at the average GPA. All right, so quick vocabulary check. The 100 seniors make up one possible sample. The sample mean is 2.5470, and the sample standard deviation is 0.7150. So mu, which is our parameter, is the true mean GPA of a senior in Virginia, And X bar, which is our statistic, is the mean GPA of a senior in Virginia in a simple random sample of size 100. Okay, so this is specifically from an SRS of size 100. To calculate the value of the population or the parameter, we find the mean of our sample, or X bar. So keep in mind, just remember that if we pick different samples, then our statistic X bar changes. Okay, so this is like thinking about your graph. Okay, so this is thinking about my graph. And if I take a sample of 100 seniors and I find their GPA, one average of 100 seniors, their GPA might be 2.5. Another, the average of 100 seniors, that one might be 3.9. The other average might be 3.0. Maybe we have a group of 100 seniors where the average is 3.1. Maybe we have another group of seniors whose average is 2.9. So when we pick different samples, the value of our statistic changes. Okay. If you graph the values of X bar for all possible samples of size 100, so if we took all of the seniors in Fairfax County and every single solitary possible combination of 100 seniors, then you will have constructed the sampling model or distribution of sample means. So what will the sampling model look like? Remember that each X bar value is a mean. So everything in my sampling distribution is a mean. Means are less variable than individual observations because if we're only looking at means, then we don't see any extreme values, only average values. So we talked about, I asked you the question earlier, why is the sampling distribution going to be less spread out than the population? Well, this is why, because each one of these values is a mean. So we found the average. We're averaging out the low and the high extreme value, averaging out the low and the high extreme value, okay? And then we're taking the average again to find the average of all of your averages. So we're not going to see GPAs that are extremely high or extremely low because this low GPA all the way down here got averaged with this high GPA up here, and it's going to put it right in the middle. We're only taking a look at average GPAs. The larger the sample size, the less variation we're going to see in X bar. So as the standard deviation decreases, the sample size increases. But remember, this does not have to do with the central limit theorem. The central limit theorem only has to do with the shape. Okay, because remember, if we take a look at our standard deviation, okay, it is the population standard deviation divided by the square root of n. Okay, so as that sample size increases, if the sample size is large, it's going to be approximately normal. Is going to decrease. We have to know that that's greater than 30 by the central limit theorem. Okay, if the sample is from a normal population, then the sample means will be approximately normal. Remember, don't ever say normal because it's never going to be perfectly normal because our data is discrete. Normal distributions are continuous. Okay, so it's never going to be perfectly normal. By discrete, I mean they stop. So you could have an answer of 1, 2, 3, 4, 5, but normal distributions are continuous. They're including every single number between 1 and 5. Furthermore, the mean of the sampling model, mean of X bar, will equal the true population mean. Okay, so what does that mean? That if I have my sampling distribution of all of my 100 seniors, okay, what is the mean of the sampling distribution? The mean of the sampling distribution, I know it's the mean because I have it denoted by that, is equal to the mean of the population. The standard deviation, so the standard deviation of my sampling distribution, denoted by that X bar there, is equal to the population standard deviation divided by the square root of n. Okay, please make sure that you include this. So if the population is 10 times the sample size, you need to prove that in order to use that standard deviation. This shows that my individuals are independent. Sample means. What was the central limit theorem? The central limit theorem stated, if I draw a simple random sample of size n from the population with mean mu and standard deviation sigma, If n is large, specifically greater than 30, the sampling model of the sample means x bar is close to normal. So basically that's just saying if your samples are greater than 30, then your sampling distribution is going to be approximately normal. Okay, so this is your notation for that, approximately normal with a mean of mu, standard deviation of population divided by the square root of n. Okay, same formulas that we just talked about with your mean and standard deviation. What does the law of large numbers tells us? Basically, the central limit theorem is based on the law of large numbers. So the law of large numbers tells us that as we draw observations at random from any population with mean mu, as the number of observations increases, the sample mean x gets closer and closer to mu. Well, think about that. Think about how we talked about the law of large numbers with the coin flipping. So if you flip a coin 5 times, is the probability of heads and tails necessarily 50-50? Well, not really. But if I flip it 5,000 times, the probability of heads and tails is going to get closer and closer to 50%. Well, the same thing happens here. So as I take larger and larger samples and take the mean of each of those samples, the mean of the distribution is going to get closer and closer to your population mean. Example. So the height of young women follows a normal distribution with mean of 64.5 inches and a standard deviation of 2.5. Now notice there's no X bars or P's hats here. So this is telling us that this is looking at individual young women. So if I was to draw that, it would be individual women in my distribution. Okay. The first thing I'd like you to do is find the probability that a randomly selected young woman is taller than 66.5 inches. Okay. I want you to define the random variable. So when I say define the random variable, you're going to say like the probability that x is greater than something. What is x? Calculate the probability. That means draw a picture, use your z-scores, answer in context. Then I want you to find the probability that the mean height of a simple random sample of 10 young women exceeds 66.5 inches. Okay, now read carefully between the differences between these two. Okay, and I'll be going over them, but I want you to think about it. What is the difference? That one, you're going to check the conditions. This is giving you a hint. Calculate the mean and standard deviation for the sampling distribution. I want you to think about why I'm asking you to do that. Calculate the probability, draw a picture, use z-scores, and answer in context. So take a minute, pause this. I want you to try these two and see if you understand like what is the difference between them. Okay, so let's take a minute and look specifically at the differences between these two questions. Okay, so this is why it's really important to make sure that you understand what the question's asking. Question number 1 says find a probability that a randomly selected young women. What does that tell you? That tells you that I'm looking at an individual. Okay, so an individual, that means the distribution that I'm looking at is a bunch of individual women and looking at all of their heights. Also notice the notation. The notation is the mean of 64.5. That is the individual. That's the mean of all of those individuals. And the standard deviation of all of the individuals is 2.5. Look at the difference between the wording here. It says find the probability that a mean height of an SRS of 10 young women exceeds 66.5 inches. Okay, so that is no longer taking a look at individuals. Since we're taking an SRS of 10 young women, this is telling us that I'm looking at sample means. Okay, how did I know that I was using means over proportions? Because it says mean height. Okay, so that would be, this sampling distribution would be the mean of all of those women's heights. So groups of 10, what are their means? Groups of 10, what are their means? And then when I describe the mean and standard deviation, I have to put that X bar there to say, hey, I'm looking at a distribution of all of the average heights of 10 women. Okay, so hopefully you notice the difference between question 1 and 2. Question 1 is not a sampling distribution. It's the distribution of a population. Number 2 is a sampling distribution. 1, find the probability that a randomly selected young woman is taller than 66.5 inches. How did I know? Because it says A, so I know that I'm looking at an individual. Okay. Okay, so how do I do that? Number one, define your X. What is X? It's the height of a randomly selected young woman. Okay, make sure you always, this is the same work back, when we did z-scores a way long time ago. So X is normally distributed with a mean of 64.5 and a standard deviation of 2.5 given to us in the question. All right, so then you're going to find your z-score because we want to know that it's taller than 66.5 inches. So the probability that X is greater than 66.5, find the z-score of that, okay? And then, which is 0.8, the probability that z is greater than 0.8 is 1 minus this, or you don't even have to show this work here. You can just say the probability that z is greater than 0.8, use your graphing calculator, and give it 0.2199. So the probability that it's greater than 0.8, which is all over here, is 21.19%. So the probability of choosing a young woman at random whose height exceeds 66.5 inches is only about 21%. So that is choosing one young woman. How does that look different from the second? This is not a sampling distribution. You are not looking at the mean height. You're just looking at the height of one randomly selected young woman. Please make sure you read carefully. Okay, so let's take a look at the same question. Let's take a look at question 2. All right, what is question 2 saying? Find the probability that the mean height of an SRS of 10 young women exceeds 66.5 inches. So that's taking a look at the average of 10 women. Well, number one, how did I know this was a sampling distribution? I knew it was a sampling distribution because I'm looking at the average height of 10 women. We have two sampling distributions. We have proportions and we have means. How did I know I was looking at means? Right here, I'm finding the mean height of a simple random sample. So when I have my sampling distribution, it's a whole bunch of X bars. So 10 women find their average height, 10 women find their average height, 10 women find their average height, 10 women find their average height. All right, how am I going to do that? Okay, remember that with your conditions, so you have 3 conditions you always have to met. Get used to these. You use them in proportions. You use them here. You're going to use them for the rest of the year. 1, make sure you have a simple random sample of 10 women. Why? Why does it have to be a simple random sample? Can't make inference about the population if it's not a simple random sample. Okay, 2, has to be independent. When I'm finding the standard deviation of the sampling distribution, each observation has to be independent. That's the population 10 times the sample size in context. So there are more than 10 times 10 or 100 women in the population. The sampling distribution of the sample mean is approximately normal since the population is normal. So you have to show that it's normal because I can't use these scores if my sampling distribution is not normal. I have my conditions. Since I have my conditions, all right, let's find it. Number 1, you have to find the mean and standard deviation. Remember the mean of your sampling distribution, so the mean of this is the mean of the population. So the mean of X bar is 64.5. Use the notation correctly. X bar, I'm looking at a sampling distribution. Standard deviation of the sampling distribution is 2.5 over the square root of 10. You have to show that work. Okay, equals 0.79. All right, so the average height of the sampling distribution is 64.5. The standard deviation is 0.79, which is much smaller than my 2.5. Okay, so I know it's approximately normally distributed, mean of 64.5, standard deviation of 0.79. What comes next? Your probability statement. Okay, the probability that your sampling distribution is greater than 66.5. Well, notice here that is no longer an X. Okay, in the last question, we wrote the probability that X was greater than 66.5. Well, this means individual. This means my samples of 10. So you have to be careful with that notation. Make sure that you have X bar there. Okay, then we have to turn that into a z-score. So there's your z-score, sample minus mean divided by the standard deviation equals 2.53. Back to the same old kind of questions we did before. What probability are we finding with z? That z is greater than 2.53. Use your calculator to get the answer, which is 0.57. All right, now take a look at our conclusion. It is very unlikely, so there's a less than 1% chance that we would choose a simple random sample of 10 young women whose average height exceeds 66.5. So keep in mind that that's a simple random sample of 10 young women. It's not an individual. Go ahead. I'm going to let you guys read this one on your own. So this is a sample mean distribution of sample means, since we're looking at the mean height of 10 young women. Answering the questions. Get used to reading stuff carefully. We'll go over the answer and you'll see how you did. Okay, just make sure as you are reading it and answering the questions, make sure you're understanding if they're asking for probability for a single sample, sample proportions, or sample means. Okay, let's take a look at the answer and see if you're able to figure it out and understand whether we're talking about a distribution of a population or a sampling distribution. Here's what we knew from the problem. The information from the problem we have from the population. We knew that the population mean for servicing air conditioners was 1 hour and the standard deviation was 1 hour, right? Because it said that it was about 0. Your company will service an SRS of 70 air conditioners. We've budgeted an average maintenance time as 1.1 hours per unit. Will this be enough? Okay, so you have to decide, is this a sampling distribution or the distribution of individuals? Hopefully, you took a look at the fact that this said SRS of 70 air conditioners and understood that when they've budgeted an average of 1.1 hours per unit, when I answer this question, I'm going to be looking at the sampling distribution, and hopefully you understood that it was of sample means. How did I know it was sample means? Because I'm talking about average maintenance time. What is average? That's sampling means. Okay, so you said to yourself, okay, now that I know that I'm talking about sampling means, I got to do my 3 conditions. Hopefully you're getting used to these by now. Simple random sample, in context, 70 air conditioners. There's most likely more than 10 times 70 or 700 air conditioners. Therefore, the sample is independent. Okay, and I'm just going to highlight this. Number 1, this is in context. Okay, with your work shown, you need to make sure you show this, and then in context, and then also make sure you state therefore independent. You can also use your little math symbols and write therefore independent if that's helpful. Okay, and then you want to make sure that it's approximately normal. It said specifically in the problem that it was strongly skewed to the right. However, remember from our central limit theorem, n is equal to 70, which is greater than or equal to 30. You have to show that. You have to state 70 greater than or equal to 30. So by the central limit theorem, the sampling distribution will be approximately normal. You could also just write it as 70 is greater than or equal to 30. Okay, so by the CLT, or the central limit theorem, it's approximately normal. Okay, that's also fine. Okay, but that's the important information that you have to include. All right, so what work do I need to show? All right, 1, I would suggest drawing the graph. Okay, we have a budgeted average maintenance time of 1.1 hours per unit. I want to know if this is going to be enough. So what's the probability, basically, that it's going to take longer than 1.1 hours? If it's a pretty high probability it's going to take longer than 1.1 hours, then it's not going to be enough time. Okay, so remember that you're finding the mean of the sampling distribution right here. So the mean of this sampling distribution is equal to the mean of the population, which is equal to 1. All right, and you can just write the mean of x bar is equal to 1. So this tells you that I'm looking at the sampling distribution when I have that x bar. You also don't have to show this part right here. You can just say the standard deviation of the sampling distribution, that's why you have the x bar, is 1 over the square root of 70. Remember, square root of 70, that's my sample size, is equal to 0.12. So the standard deviation of the sampling distribution is 0.12. Okay, make sure you include that x bar there so that they know you're looking at the sampling distribution. Okay, it's approximately normally distributed, mean of 1, standard deviation of 0.12. Okay, same work as we've shown before. I'm just going to highlight the fact that this says the probability that x bar is greater than 1.1 because we're looking at the sampling distribution. You cannot write the probability of x. Find your z-score. Okay, what's our z-score? And then the probability that z-score is greater than 0.83, you can just get that from your graphing calculator, is 20.33 or 20.33%. All right, so do we think this is going to be enough time? Let's come up with a conclusion. Sorry, let me just get rid of this. Okay, and let's look at our conclusion. So if we budget 1.1 hours per unit, there's a 20.33% chance that the technicians will not complete the work within the budgeted time. Follows a right skewed distribution with a mean of 45 and standard deviation of 35. Okay, just make sure you read it carefully and understand what they're asking for. Go ahead and pause it, and when you're ready, go ahead and press play. All right, let's see how you did. Okay, so number one, you hopefully you got this down by now. Taking a look at your information, you don't have to write this portion down, it's just helpful. We have the mean of the distribution of the population and the standard deviation. We know we have an SRS of 50 students that have an average of 25,000 ticks per day. Okay, and then each group, so here's the tricky part for this one. So we have an SRS of 50 students that have an average of 25,000 ticks per day. It should be 2,500. So each group of 50 students is really sending 2,500 divided by 50 or 50 ticks per day. Okay, so that's a little bit tricky in understanding that the 50 students have an average of 2,500 ticks per day. So if we're looking at the individual groups of 50 students, we have to divide that. All right, so our conditions, we have a simple random sample of 50 students. Okay, that allows us to make inference. There's most likely more than 50 times 10 or 500 students, therefore independent. Make sure you include that independence. By the central limit theorem, the distribution is approximately normal. So central limit theorem, approximately normal, 50 greater than or equal to 30. That's what's important. And then once again, finding your mean, your standard deviation of your sampling distribution. Mean is 45, standard deviation is 4.95, okay, because you're taking your sample or your standard deviation of 35 divided by your sample. Make sure you include that x bar. Okay, what do we want? We want the probability that x bar is greater than 50. X bar, not x. Z-score, sample minus your mean divided by your standard deviation is 1.01. Understand that this is the standard deviation from your sampling distribution, not the 35, okay, because I'm specifically looking at the sampling distribution here. The probability that z is greater than 1.01 is 0.1562. So there's a 15.62% chance that a random sample of 50 students will have sent over 2,500 texts in the last day. Okay, so make sure you include that concluding sentence. Okay, go ahead and try this one. Okay, so this one is a little bit different. Our question is asking us how many axles would we need to sample if we wanted the standard deviation of the sampling distribution for the sample means, so we know we're talking about sampling distribution of sample means, to be 0.005 millimeters. Justify your answer. So did you figure out that you need to look at the formula for the standard deviation of the sampling distribution? So we know that a grinding machine in an auto parts prepares the axles with a target diameter of mean 40.125 millimeters and the standard deviation of 0.002. We want to determine how many axles are needed to sample if we only want the standard deviation to be 0.005. So this is telling us, this is now looking and trying to find our n value, not looking at a probability. However, we know, since it's asking how many axles do we need if we want the sample standard deviation to be 0.005, we know in this case we're looking at a sampling distribution because how many axles in a sample, okay? We know the formula for a sampling distribution is the sigma, or your standard deviation of the sampling distribution, is the population standard deviation over the square root of n. Well, let's see what we have. We know what we want the standard deviation to be. We have the population. What don't we know? We don't know the n value. Okay, so we just fill in. We know that we want the sampling we want the standard deviation to be 0.005, so that comes from right here. Okay, we know the population is 0.002. And we're looking for n. So let's just rearrange this mathematically. How did the n get on this side? Well, I took 0.0005 equals 0.002 divided by the square root of n. Okay, so what you could do, honestly, is just cross multiply since you have a proportion. And you would end up, when you cross multiply, you would end up with 0.0005 times the square root of n equals 0.002. Okay, divide both sides by the 0.005 to get n alone. Okay, that cancels each other out on this side. Okay, you get your answer. However, you get the square root of n is equal to 4. Remember, to simplify that, you have to square both sides, and then you get n is equal to 16. Okay, make sure you answer the question in context. So we need to take samples of size 16 if we want a standard deviation. We learned how to find the mean and standard deviation of a sampling distribution of a sample mean. Please make sure you check the 10% condition before calculating the standard deviation. Explain how the shape of a sampling distribution of a sample mean is affected by the shape of the population. And if appropriate, we can use our normal calculations to calculate the probabilities involving sample means as long as we show our conditions are met.